That's okay. People can miss that part. Okay. So this is a cartoon representation of a spectrum. I will just go over what's on each axis in case you're not familiar with these. So this particular spectrum has scales of time on the x-axis, so frequency. So we have fast things on the right and slow things on the left. And on the y-axis is just the amount of energy that is contained in that scale. So this one is like you're making a frequency spectrum of velocity, which when you square it to make a spectrum gives you kinetic energy. So these are some of the same things that were in those bubbles on the last slide. Mesoscale is going to be all the way on the left at low frequencies, all the way on the right at high frequencies will be turbulent dissipation. So kinetic energy can move in either direction on this spectrum of things. When it moves to larger scales, we call that an inverse cascade. And when it moves to smaller scales or higher frequencies, which tend to be connected, we call it a forward cascade. Also upscale and downscale works and is more intuitive. And so one of the things about the ocean that I think Kaiki may not have pointed out directly, but definitely touched on, was the fact that at larger scales and lower frequencies, so submesoscale, mesoscale, I need to stick with power. Okay, so at these scales, kinetic energy cascade is well modeled by 2D turbulence, which is like if you can picture just eddies moving around in a flat plane, we don't care about what's going on in the z direction. And that type of turbulence tends to move energy towards larger scales. And that is different than what is going on in internal waves, which you need to think about in 3 dimensions to understand where their kinetic energy goes. And then 3D turbulence is all the way down on this end, which is like turbulence that is the same in 3 directions, not just 2 directions. And then you get this interesting region in the middle where you have like near inertial waves and tides. And I've seen studies talking about them moving energy both upscale or downscale, depending on exactly what's going on. So that's like the wacky world of submesoscale instabilities that Kaiki introduced us to. And he showed also a diagram of kinetic energy cascade where you have sometimes energy moving to smaller scales, sometimes energy moving to larger scales. Yeah, so that's sort of what connects the realms of 2D turbulence and 3D turbulence. So this is a 2-dimensional plot of all the things I was just saying from this great, this is actually from an observational study, which is pretty cool, this one. And so this is a 2D spectrum. So the last one we were looking at had frequency on the x-axis. This one has frequency on the y-axis and wave number. So like the number of oscillations per unit space is kind of what we mean by wave number. I'm sure a lot of you have heard of that before. So large scale things are on this side, small scale things are on this side, and slow things are down here and fast things are up here. So like a mesoscale eddy would probably be in this region. And 3D turbulence would be up here. So the thing that I mostly wanted to point out with this picture is that ocean kinetic energy spectra tend to be red, which is like an analogy with visible light that basically just means that there's more energy in the slow, large things, and it decreases linearly towards the fast, small things. So there's a couple of notable exceptions to this linear trend of redness, which are tides and near inertial waves. So those are the guys that you can see right here. So you can see that it's at 1 frequency. So this is the semidiurnal tide. It's at the twice per day frequency all the time, but you can see it at many different wave numbers. And similarly with inertial oscillations or waves, you can see them always at the inertial frequency, depending on your latitude, but at multiple scales. And this is like 4 times per day. It's like a harmonic of the semidiurnal tide. Yeah. So we're mostly going to talk a couple more slides about large scales, but we'll mostly talk about small scales today. So this is an even more complicated plot that I'm forcing you to look at. And it's showing kinetic energy cascade where red is a forward cascade and blue is an inverse cascade. So blue, wherever there's blue, energy is going towards larger scales. Wherever there's red, energy is going towards smaller scales. And then this is actually latitude on the y-axis and length scale. So big things over here, small things over here on the x-axis. And this is from a really cool modeling study that was quantifying the cascade between scales using this coarse graining method that we might talk about later. So other things to point out in this plot is that this black line here is where the Rossby number equals 0.1, which is a transition into the submesoscale. So like all those wacky Kaiki submesoscale dynamics are going on right around this black line. And we can also see that that pretty reliably shows where the kinetic energy cascade is transferring from upscale, blue, to downscale, red. And that's pretty cool because that lines up with what we were expecting to see with this transition zone between 2D turbulence and 3D turbulence. You can see that there are definitely some exceptions, and there's a lot more going on at large scales than just all of the energy goes to larger scales forever, and that's it. And this paper was pretty cool. It was talking about how this reversal of that, so this transfer of kinetic energy to smaller scales, has to do with the large scale currents in the ocean squishing up against continents. And like whenever the large scale currents are interacting with boundaries, that can affect the direction of energy cascade. I thought that was pretty cool. The analogy they were using was like a piston. So like if you ever took a physics class where like you have gas being compressed in a piston, it spins up faster. And so that would be the time period when kinetic energy is going to smaller scales. And it would be similar to a large scale current encountering a boundary. And that's the piston that's sort of pressing the eddies together. And you get cascade downscale. Anyway, and there's also lots of cool things going on with latitude in this plot. So like you can see, you can see the atmospheric imprint. So he was arguing that the change of the direction of cascade also lines up with the cells of overturning the atmosphere. I have no idea how that works, but I thought it was super cool. If you only take one thing away from this plot, just remember that this delineation here of the submesoscale lines up with where you see energy going upscale or downscale. Yeah. Okay, so that's pretty much all I'm going to say about larger scales because we are turbulence nerds here. So moving forward, we'll pretty much be looking at internal wave scales. So I should have labeled these, but these could be tides and a near inertial peak. And what happens at scales smaller than this is in a time mean, you have kinetic energy cascading forward towards dissipation and then eventually being dissipated as heat or converted to potential energy. So all of the energy that transfers downscale either is dissipated by friction, mixing, like we've been talking about, or that energy goes into taking the deep water at the bottom of the ocean and moving it back up. Yeah. So we'll be talking about what processes do that moving of kinetic energy downscale, and then what pathways kinetic energy takes on its way there. So firstly, the processes that move kinetic energy towards smaller scales and eventually turbulence. Ankita and Kaiki talked a lot about instabilities this morning. So at any one of these scales, you could have an instability like a shear instability or a convective instability if the criteria are met for that instability to occur. And then that can very rapidly transfer energy to dissipation. Alternatively, in sort of like an open ocean, nothing is causing an instability to happen at this scale, you can have internal waves interact with each other and move energy to a scale that is at a smaller scale or a higher frequency. And that we call that a wave-wave interaction. So the sort of accepted paradigm of like how energy gets from forcing scales, which are the tides and the winds, down to dissipation is until an instability occurs, the energy is just passed from one wave to another. Yeah, and that results in a bulk transfer of energy downscale. So in like linear wave theory, if we had nothing but completely linear waves in the ocean, you would be able to separate all of the energy at each frequency. And if that were the case, if there was no nonlinearity, there couldn't be any exchange of energy between waves. But when we expand linear wave theory to allow for weak nonlinearity, that is what allows the transfer of energy between two different waves to occur. And we can model that as these resonant triad interactions. So the basic idea is that a wave of one frequency and scale interacts with a wave of a different frequency and scale, and a third wave is born. Yeah. So this idea that we can understand the way that energy is cascaded downscale results in something called the fine scale parameterization, which we'll definitely expand upon in more depth, and you'll learn how to do them in week 3. But the idea is that if we can understand the way that energy is transferred between waves in a bulk time average sense, that we can measure the larger scale shear and strain, and then use that to predict how much turbulence would be happening. Because we know how much energy is in the internal waves and how they pass it downscale, we can predict how much dissipation there will be. So I wanted to do a little bit of like a physical intuition building activity with internal waves. So this is another form of the dispersion relation for near inertial waves that we've seen in many forms throughout the week. But just talking about like how an internal wave actually moves, like I don't know how many of you took Jen's waves class or another waves class, but you've maybe seen this dance before. So like, and you saw the video that I should have gotten the same video as Keiki, but basically like you have a wave vector that is propagating downward and the phase is propagating in the opposite direction. And what that means is like, if you are like a little particle of water and this wave energy encounters you, you just do a little circle, or an ellipse. And the circularness or ellipticity of that motion depends upon the frequency of the wave. And the angle that the energy propagates at depends on the frequency of the wave. So like if there's a wave and the phase is going this way, and I'm a particle that this wave energy passes by, I do a little circle, and then my partner does a little circle, and these should have been going in opposite directions. This results in layers of shear. So we'll look at a lot of data this week, and these layers of shear particles from all these little circular motions next to each other stack up, and that's sort of what the signature looks like in velocity. So we can tell from the dispersion relation that the lowest frequency, unless there's some effect of vorticity or tilting isopycnals, we're going to pretend that there's not. And this is just a simple case where the lowest frequency of an internal wave is the inertial frequency. So at that frequency, particles move entirely in the horizontal, and the angle of their displacement is just horizontal. So that's this case. This is the lowest frequency. Opposite to that, the highest frequency is the buoyancy frequency. So that's the case where, because the particles are just moving straight up and down, and sort of like, I guess in the limit, they're not making an ellipse, they're just making a straight line. Yeah, that's this case. So the restoring force in that case is just buoyancy. You're a particle, you move up, the water is less dense, so you want to sink, and then you sink and the water is more dense, so you want to go up. So that's this opposite case. And the spectrum in between these is where all the internal waves exist. So for the purposes of this activity, think of these horizontal lines as the lowest frequency and these vertical lines as the highest frequency. The other thing that's going on is wave number. So that is just describing the vertical and horizontal extent of the internal wave. So because this board is not infinitely wide and internal waves tend to have large horizontal scales, we're only representing the vertical wave number in this cartoon depiction of internal waves. So low wave number, high wave number. If this is confusing, just think high wave number, more waves can fit in the same space. Yeah.
I can see as a beam, for example. That one it could be a beam, because I've seen figures from models, so you can see these beams like reflecting on the surface on the bottom. So when you see the face, you can see the different colors. So I don't know if you can see this images as a beam in those figures. Like you have the face in one direction, another direction is the same as those colors. Is the representation?
Yeah, I think so. Are you talking about like ray tracing?
Yes.
Figures?
Well, so you can see both colors interact with each other and changing a different section of the picture because the faces like rotate. I don't know if it's difficult to imagine, but in I understand that how large is the beam is the long, how long is the wave number, the wave number. So
Okay.
it's if a beam is smaller, so it's a high wave number.
That's cool. I've actually looked at ray tracing figures before, but I've never seen somebody try to represent the wave number in the width of the beam.
It's what I can imagine. Look at that different, but I don't know if it's correct.
Yeah. Yeah. What I'm building up to is just trying to build a little bit of physical intuition for how internal waves make water move. And I'm gonna, in a couple of slides, show you different cartoon depictions of waves, and you're gonna have to describe what the frequency and wave number is. So just remember that frequency depends upon the angle. The maximum frequency is vertical, the minimum frequency is horizontal, and wave number is how squished or stretched they are.
Yeah, sorry.
Yeah.
So like the colors are representing what?
Okay. So the colors are just representing different layers of velocity. So like as the So if you took like a vertical profile of velocity, you would see the vectors kind of turning with depth as the wave did its little ellipses. So like as the wave propagates, it makes the water move in these little ellipses, and that causes the velocity vector to turn with depth. So you would have like, this is kind of hard to draw. Okay. Something like, all right, I'm failing pretty hard at drawing this, but can you imagine what I'm saying? Like you would see the velocity vector turn. Okay. And so that causes these patterns of shear. Like as you have one slab of water moving in a different direction as the slab underneath it, that causes shear. And so when you measure, when you get ABCP data in the ocean, sometimes it's hard to see the signal of an internal wave with just velocity, but if you plot shear, it can come out a lot clearer. And so this is just a representation of the different layers of shear that you would see. Yeah. Is that a question or just a thought?
No, sorry.
Cool. And it's also just a representation of the period of the wave, I guess. So like if the turning velocity vectors don't help you interpret it, you could just think of it as a wave signal, and these are the two layers that we're looking at. And all I'm really trying to show is that for the higher wave numbers, one wave period fits into a smaller space. Okay, so back to wave-wave interactions. One wave interacts with another wave and a third wave is born. Or in this annoying case, one wave experiences an instability and two different waves are born. So does anyone want to take a stab at describing what has happened in this wave-wave interaction? And if you already know about parametric subharmonic instability, then maybe give others a chance. So like I'm looking for somebody to look at the shape of these cartoons that I've drawn and tell me what, if anything, is happening to the frequency. So like this wave creates a wave, two waves that are slightly different. So what has happened? You think the frequency is higher to the left?
Yeah,
What makes you say that?
because it's more the inclination is bigger.
Yes. I was just checking that that was exactly what you saw because that's super subtle in this case. I think it's pretty subtle, but that did happen. Yes. Okay. What else happened?
Big number. Pieces.
Yeah. Yep. So you have one wave that has turned magically into two different waves of higher wave number and lower frequency. So congrats, we got it. So the description of this parametric subharmonic instability is a low wave number wave decays into two high wave number waves of half the frequency. So we're basically just building sort of a zoology. There's like three different significant types of wave-wave interactions that you'll see in literature sometimes. And so we're seeing if we can build the description of those without knowing what it is initially. Okay, let's try to look. So we're starting here and we're adding this wave to that wave. We're getting something like this. What has happened? So like, maybe let's start with the left-hand side of the equation. How would you describe these two waves in relation to each other?
So the far left, right is closer to the n value, right? The maximum, and the other one's slower because it's not vertical. And well, I got.
So you've got a high frequency wave and a low frequency wave. What else is different between these two? Yeah, okay, totally. So you have a high frequency wave interacting with a low frequency wave of lower wave number. This is kind of, there's a lot of things you can get mixed up here. Okay, and the result is
Higher frequency wave with higher wave number.
pretty similar wave number. This one doesn't necessarily, yeah, so high wave number, high frequency wave scatters off a low wave number near inertial wave and generates a slightly lower wave number, also high frequency wave. Induced diffusion. Okay, last one, and then I will stop torturing you for now.
Wait, sorry.
Yes.
Going back to the other one.
Yeah.
I wouldn't think that you would get a higher frequency. I guess I would imagine that it'd be in between the two, which is that the case?
I think it is the case. So it's also a high frequency wave and it's slightly lower wave number.
Yeah.
I think that this frequency is similar to that one, and I think it's probably slightly,
It's a little
yeah.
smaller.
I think the more significant part of this induced diffusion thing is that the wave number is lower. Yeah. Basically, we're like passing, you have like a high frequency wave that's scattering off a near inertial wave and then passing energy to lower waves.
Can you repeat what you just said?
Okay, I said a high wave number, high frequency wave scatters off a low wave number near inertial wave and generates a slightly lower wave number, high frequency wave. These all seem unrelated, don't they? Okay, last one. Who could take a stab at trying to describe what has happened in A plus B equals C?
So all frequencies are almost the same, right? The left,
Mhm.
the difference is the wave number
Mhm.
is lower in the farther left.
Yep.
So they create a lower wave number.
Mhm.
And also lower frequency.
And not even-
And also lower frequency.
oh,
Yeah. So I don't have a good way of representing horizontal wave number in this one, but two waves of a similar horizontal wave number and large separation in vertical wave number generate a low frequency wave of much larger wave number. Zach is,
That's not the definition of loss, it's scattering noise. Like the one that I'm familiar with is, it is a scattering of a high frequency wave with a low frequency wave, but the resultant wave has an equal and opposite vertical wave number to the initial high frequency wave. So you're not
Or an
really
opposite.
moving energy, so your triad would be like, the wave vector of the low frequency wave is like almost perfectly vertical.
mhm,
The wave vector of the high frequency wave points like this, and then the wave vector of the resultant wave points like this. So
Yeah.
these two have the same vertical wave number. It is going in opposite directions,
yeah,
and so you're not really moving energy across vertical wave number. At least that's the definition of Thomas and relativity.
okay.
That I typically see in literature.
I appreciate that. I pulled this from McComas and Brotherton this weekend, but perhaps I pulled it wrongly. I trust Zach more than I trust myself on this topic. So if that's the case, then ignore this diagram and I will try to fix it in the notes. Thanks, Zach. All right. So all three of those types of triad combine to create a bulk transfer of energy to smaller scales and higher frequencies. a lot of theoretical studies have argued that interactions that transfer the most energy to dissipation, like the most important interactions for downscale energy cascade, are between high mode waves, which contain the most shear, and low mode waves, which contain the most energy. So there's this idea of locality of like, you can describe if an interaction is local based on how close two waves are in wave number frequency space. And so like a lot of the classical literature has used this paradigm of like large scale separated interactions are the most important for transferring energy downscale. But that's kind of still an area of debate. So there are a lot of recent like numerical method and modeling studies that are showing that local interactions are actually more important than we thought. So this one is predicting that 63% of the, so this is like induced diffusion, parametric subharmonic instability, and elastic scattering. And then the dark portion of it is how much of that would be considered local. And so 63% of the interactions that are moving energy downscale actually are local. And so I think that this recent shift in the way that we're thinking about it has a lot to do with like being able to model things at higher resolution for longer amounts of time, versus leaning more heavily on theory. But it's totally not my area of expertise. So, yeah.
Cool.
Okay. Moving on from wave-wave interactions to like the mechanisms that pass energy between scales. I'm going to do sort of a tour of the forward kinetic energy cascade in spectral space. So like what pathway does energy take on its way down scale? And we're going to be using the shear spectrum because that happens to be a good example of the different shapes that the shear spectrum makes correspond to different regions that have different dynamics. So it's a tool that we use pretty often in observational oceanography to like look at the different dynamical regimes of the energy cascade. So we're just going to build this figure up over time. So first off, the x-axis is wave number. So this is different from the last cartoon spectrum that we looked at, which was in frequency space. So large scales are on the left, small scales are on the right. X-axis is going to be energy density. So, well, shear energy density. So the numerator, this is just shear divided by cycle per meter. So it's like the amount of shear in a cycle per meter, or shear squared. That's why it's shear energy. So like I said earlier, the areas that have different shapes of the spectrum correspond to different dynamics that are going on. So two of those areas have common names that you might hear people use in like literature and casual conversation. So this area on the left that has this flat slope is called the internal wave continuum. So that's where internal waves are happening. That's where your wave-wave interactions are happening. The lowest boundary, so the largest scale leftmost boundary of this region would be the lowest mode of an internal wave that you could have happening. So depending on your forcing, that could be either an inertial wave or an internal tide, or I don't know, some other low frequency wave, but pretty much those, because the things that force the ocean are the tides and the wind. And then on the right, your higher, smaller scale frequency. I often switch between wave number and frequency language, but I need to be more careful with that. So the smaller scale boundary on the right, higher wave number would be whatever your critical scale for instability is. So if this is a case where you are experiencing wave breaking due to shear instability, this could be for a normal thermocline, this could be like a 10-meter scale. And that's the example that we're going to use. But if you have a convective tide breaking event, that scale could be different. So the other area of the spectrum that has a common name is the inertial subrange. And this is the scale at which we expect 3D turbulence to be happening. So it's sort of this bumpy thing at the end. The largest scale on the left that borders this section is the Osmodov scale, named after some guy. And so that's the largest scale of 3D turbulence. And then the smallest scale would be the scale at which viscous dissipation becomes dominant and the kinetic energy is dissipated. Yeah, so, and this tends to account for like 10 centimeters to 1 centimeter scales, which is a really uncommon scale to measure things at in like most oceanography. Like if you have like a shipboard ADCP, you're not going to get anywhere close to like being able to directly measure these scales. And so that's why we have some really specialized instruments that help us make a shear spectrum at the scale, which we'll learn more about tomorrow, I think. Yeah, so this is the internal wave continuum. This is the inertial subrange. This sticky area in the middle with the -1 slope doesn't have a common name that I am aware of. And it has the least that is sort of known and agreed upon about the dynamics that are going on. There's a lot more like theory developed about the other two sections. So when your kinetic energy increases, so if you have more energy contained in shear at all scales, the level of the other two areas increases. So like the spectrum will move up in these two, but the level will stay the same in the -1 slope region. And that's just a really fun little mystery as far as I'm aware. So just to review, here is the whole spectrum that we have built. The reason why we care about its shape is because it indicates different dynamics that are going on. And also because it's so predictable, it allows us to use observations of larger scale velocity. So if we can observe the velocity up here and compare the level of the spectrum to like this theoretical shape, that can enable us to predict how much dissipation is going on down here. So it's important that we know in theory what the shape of the spectrum should be. And that's the idea of fine scale parameterizations that I talked about earlier. So like parameterization just means getting something out of a model that isn't included in the dynamics that it's actually computing, and fine scale would be referring to like the scales of internal waves that are happening up here. So if you can measure the fine scale, you can parameterize the dissipation. Let's actually stop here. Are there any questions? Yeah.
Yeah, so does the shape of the shear spectrum change if you're doing a frequency set of wave number?
Yes. And I don't have that one on me.
But the group one should find epsilon is still one wave number?
Yes. Yeah. Questions, thoughts? I see some, yeah.
What is it?
Yeah, Heike asked if the shear spectrum in frequency space has a different shape, and yes, it does, but I don't have it on me right now. But it's the shear spectrum in wave number space that is used to create, compute epsilon, which we'll get into tomorrow.
So for I was just thinking about shear, and you're doing this over a depth from like kilometers to centimeter calculation, which if I remember shear correctly, it's like the change of density over the vertical, right? And so I guess how are you like, is this taken like at certain depths to get this, you know what I mean? Or is it like an average of the two? It just seems like, yeah, there's like a lot of variability to cap it depending on what layer you're at.
Yeah, so shear is change of velocity with depth, or any dimension, but this isn't depth. So if we take a profile of velocity over any length, but let's say we have surface to bottom, the way that we make a spectrum is by doing a Fourier decomposition. So like we are doing some math magic and figuring out how much energy is contained at different scales. So up here, like this is the amount of energy that you would expect to see in shear at 1 kilometer. So like it's not taken at one depth, it's taken over. You would need a vertical profile to make a spectrum like this.
Okay.
I don't know if that helped. Did that help at all?
I think it does help, because and then what are you choosing? Like doing like the fast Fourier transfer, what are you choosing for your like windowing?
It depends upon the situation. So I guess we could say that if you wanted to measure it, so like the higher end of this depends upon the window length, and then the lower frequency depends upon the yeah.
Yeah.
So like yeah.
This kind of spectrum would be made from like, you know, imagine a velocity profile that you would have with like a full ocean kind of thing, like all, and then you do that at a bunch of places, and then over a bunch of places, you realize that, oh, actually, you know, the shape of this thing is roughly similar no matter where we are. So there's like this shape of like, oh yeah, on the 10 meters to kilometer scale, there's typically kind of a flat shape to the spectrum. Oh, wait, and then we go into like these different inertial ranges and so must be like ranges, and you see that the there's very different, sure, but yeah, but so this spectrum was made not in time, so there was not like, well, shut the window and like do the average stuff. It's like there's a full water column velocity profile, and then we see there's very but then there's also across different locations in the ocean, the shape of something roughly like this.
So
You can think of it as like a snapshot in time, like how much energy is at any given spatial scale. It's a way to think about it.
I mean, maybe you're trying to get at the fact that there's a really big separation between a kilometer and a centimeter, and it would be like really difficult to get a spectrum that covers all these scales.
Yes, yeah.
Yeah, it is super difficult, and like hardly anyone has ever actually done it because you need instruments that are measuring at really small scales and at large scales.
Yeah.
But one of those really rad, awesome people is in our lab, and this paper is actually in review right now. So our friend Devin Northcott made this spectrum, which is like covering all the way down to dissipation basically, and then this would be the part where the spectrum kind of flattens out. So he doesn't have all the way out to a kilometer, but this was made with a wire walker, so it's like a moored or drifting instrument that like uses wave energy to sort of climb a profiler up and down a cable, and you'll probably see one in the lab tomorrow. But so he used two different settings on a Nortec 1000 ADCP, right, Austin? Yeah, Austin's nodding. And then this part of the spectrum was made with a shear probe, which measures very small scale shear. Yeah. So thank you for leading me into this example.
That was my plan.
I appreciate it. So the other really cool thing that you can see, so he took, do you know how much time was how much time of data? How many profiles? Okay, maybe a month's worth of data. He took a large time sample of data and he binned them based on how much dissipation he was seeing. So this spectrum shows really beautifully that like, so the lighter colors are where there's less dissipation going on, and then the darker colors, there's more dissipation. So he binned it based on this level of the spectrum, and you can see that it's also reflected in this area, and then it collapses onto this -1 slope region where we don't expect to see the level change. So that one is similar to this picture right here. Yeah, so. And then there's also, so this dashed line underneath is the theoretical shape that we would expect based upon theory. And then the solid lines are the data. So you can see that like, it lines up like decently well with the shape that he's seeing, like actually really well. If you look at individual spectra from observations, they don't look nearly this good. So these are like averaged over time, which is why they fit the theoretical shape a little better. Yeah. Thanks, Devin. So are we all good sort of up to this point?
I have a question. Why then the lines are not continuous?
Why are they not continuous? Because this part was measured with the Nortec 1000 ADCP on two different settings, like for measuring different scales. So because this was one instrument, it's continuous, and then this was made with an entirely different instrument that was on the same platform. So like these observations are co-located in space and time, but it's two different instruments, and there's a slight separation in the scales that they measure.
And between the ones that are in the second part?
These guys?
Yeah, these guys are not matching with the left ones, but I don't know, they have a curious curve.
Oh yeah, there's this big gap.
And they're on the right.
Okay.
Not that's right. Sorry. This started the big curve, and there is a little ones.
This guy right here.
Huh.
It's probably the noise.
You know what? No, I mean this is the noise up here, but maybe this. So I think, and maybe Austin can help me here because he was more a part of this project. But I think this is one setting on the Nortec ADCP. This line is another setting on it, and then this is the shear probe. Okay.
Okay.
Cool. Thank you. Thank you for pointing that out. I had that wrong.
This is probably just a small detail, but you have any idea why this year probe and the contact essentially so much? At least in the.
Here, at least in the high frequencies. I mean, I don't know. Do you have any thoughts, Austin? Eric also works on wire walkers, by the way.
Yeah.
Well,
I think part of
Didn't he?
it, so
Yeah,
that middle section is what we call like the plus coherent mode, so it's like kind of the like fine scale mode for it, but the reason is that like because you're having such high resolution in that area, it's still like your range is significantly shut off, so that's why like it cuts off to the left side of it, like you're not seeing as far in the water itself. And then also because of like how the instrument does its averaging, those like really low or I guess high wave number values are kind of just muddied because it's kind of right around its like operating region. So especially for like the really small values of epsilon, it is really difficult for it to actually get an accurate value of it because it's right at that kind of weird operating region of like starting to get mostly dominated by noise. Whereas the like EPSI probes, that like last bit at the end, it is specifically tuned for those like microscale features. So yeah, it's just kind of like a weird artifact of like, yeah.
It's also two fundamentally different ways of measuring turbulence, where first like the leftmost and the middle are from like acoustic ways of measuring, which Austin will talk more about later. And then the rightmost part is like with a probe that actually measures like flow, microstructure flow of the water. So there are different ways, and so there are different assumptions going into each like sections of this spectra as well.
It's not great. It's not value so I'm being good clients. What is that? We're talking about it.
yeah.
Like,
Okay.
Yeah.
Just waiting to see if there's one.
that's
Okay. So this dark color would be the highest value of epsilon. So if there's more energy in shear at these high wave number scales, like picture a more turbulent flow with like higher Reynolds number, and you have more little, like the higher the Reynolds number goes, the more turbulent the flow is, the more little eddies you have. And all of those eddies are generating shear. So like if you have a flow, then at smaller scales, you're going to be getting more energy contained in shear. That makes sense.
okay.
So like you have more kinetic energy going in at larger scales, and that's reflected by more energy being taken out at smaller scales.
Okay.
Okay.
Yeah. One thing we're gonna talk about this afternoon too is that these spectra depend on like epsilon as well as K, and so which quantity to K, but like it does also have an on epsilon. So like that's the that is like it depends on two variables, and so one of those variables is just set to plot this, and then the other variable is like to do something.
Okay, at the end of this thing, I'm not thinking of the y-axis of like shear. I was like, this is my head.
Yeah.
Okay, thank you.
Yep. Okay. So with the last few minutes that we have, I wanted to talk about some different tools that we use in observations and models to like actually quantify the kinetic energy cascade. So like when I say quantify cascade, I mean like if you have a spectrum and you want to know like at this scale how much energy is being transferred from larger scales to smaller scales, that quantity is something that people do with a big pi. And that is something that we can quantify using various different tools. So some of those tools are here. So one of them is coarse graining, which allows for strong nonlinearity. And it requires you to have a sort of 3D grid of data. So it basically takes the equations of motion and applies them to a low pass field. So you would take a field, you would take your data and low pass it. So you're only looking at these frequencies. and then they apply it to the Boussinesq equations of motion, they get a kinetic energy budget. And one of the terms in that budget is the energy transfer from larger scales to smaller scales. So that's sort of the idea behind coarse graining. It's like the selective low pass filtering method. Another one is structure functions, which I have never worked with. And oh yeah, Zach.
As is coarse graining, you're able to resolve across the whole range of scales, or is it just like large to small scale?
So this value, that if you calculate like the cross scale kinetic energy flux, would only tell you the transfer across the scale that you're low passing at.
Okay, gotcha.
And if you are using data that is like, say, you don't have anything from dissipation, you're really only resolving up to this scale. In that case, if you did coarse graining, you would be saying how much energy is transferring from these scales only into this bin.
Gotcha.
So you can't say what's transferring to scales smaller than you can see.
Okay.
Because that information isn't in your data.
Sure.
Yeah. And then has anybody worked with structure functions before and wants to say anything about them? Otherwise, we'll just leave it. Zach, are you raising your hand, or
I mean, I have.
do you want to say anything about them, or?
I don't know that I can give a great explanation. They're kind of an alternative to like the Fourier methods that are shown here, where like instead of working in the frequency or rhythm space, you're working in terms of like real space. So you're working in terms of like coordinates and time. And what you often do is you're looking at statistical moments of increments of your data. So you have observations that you've made. And the easiest way to describe it, I think, is in time. So you select some sort of time lag between the data, and then you define this difference between them, which is like a finite difference coefficient with a certain window width, and you slide that all the way across your data. Then you repeat it for a different width, and you repeat this process. And the idea is that within a certain range of time separations, the moments of those differences should obey like a power law. If the system has a power law, I feel like I just did an awful job.
That's way more than I would have said about it. I would have just said that one of the reasons why people like structure functions is that they don't require you to have evenly spaced data. And so a lot of people, for example, if you had like a cloud of floats that you had put out in the ocean, you would be able to compute the transfer of energy between scales, even though they're not evenly spaced.
I think, wasn't it also like one of Kolmogorov's laws was defined in terms of structure functions, like the Stewart law or something? I don't know. But I think it also gives you a way, well, I guess that's what you're saying, that it gives you a way of estimating epsilon through structure functions.
Yeah, so like epsilon is kind of like a transfer of energy between scales, but it's like across the bottom boundary of your spectrum. So it's all in watts per kilogram, but instead of looking at the transfer of energy from this bunch of scales to that bunch of scales, you're looking at the transfer of energy from all scales to dissipation. So in that way, all of this is sort of epsilon. Yeah.
I was gonna say, you're talking about changing scales from like only one scale to another. My understanding is that a lot of the time kind of make the assumption that the transfer energy into dissipation is equal to the transfer energy across every single scale. But like,
yeah,
we're assuming there's no jumps, that like it's all just going from along every single scale, then your epsilon is also the rate at which energy is being transferred along between.
Yeah, that actually leads me really well into my next slide. Thank you. So the final method that I just wanted to mention was like, there are different groups of people that have come up with these numerical methods that actually like simulate the wave-wave interactions in spectral space. So like if you take a box of your space in frequency wave number and you know the amount of energy there, it would take the wave kinetic equation and the collision integral and figure out how much energy is transferred from one bin in spectral space to another by like the triad interactions that would happen if your fluid was modeled by weakly nonlinear wave-wave interactions. So, yeah.
I'm sorry,
Yeah.
is that the same as the assumption that your spectrum is steady, like energies?
I think so. I don't know the exact terminology. basically, yeah, it's the assumption that have the cascade is going along every single point like in space, and it's not going from that one large scale to like a small scale directly. And if you make that assumption, then you can assume that you're like, we'll do the math in our lecture, but like basically that you go from like your every production of energy term, that like basically to your need and your like turbulent energy, you said that equals to your dissipation, and you kind of assume that because those are equal, because everything's just always going down one scale, then like if you have epsilon, you have the transfer of energy. There's a lot of stuff here.
So-
A lot of sense. We can get into it.
It's answered very well by my next.
Or it'll be answered.
I will say that I don't think that it's the same thing as being steady, because if you had, I'm gonna draw a frequency spectrum because that's what my next figure is gonna show. But if you had like, there's the near inertial tide, and here's dissipation, and here's internal waves, you could have a steady state. So like at each point in time, you could have more energy being transferred from this scale to dissipation than this scale. And so that would be a case where you had a steady state where the energy transfer wasn't changing over time, but it always was more heavily weighted towards a less local transfer of energy. Does that make sense?
Yeah, so just like energy, like if you had that picture, would that also imply that you have an equal amount of energy dissipated to lower scales as those two arrows go? Energy is.
So your dissipation could be steady and your input of energy could be steady. So like steady forcing and steady dissipation. But I'm saying that the pathways don't have to be equal from each bin in the spectrum. So the spectrum's shape is not changing over time, but the energy is being transferred unequally from different bins. Oh, this is just talking about force training. We already talked about that. Okay, so this was some data that was taken in Canyon. Sorry about how much is going on. So this blue line is a vertical average. Sorry, time. All of these individual blue dots are estimates of dissipation from a shear probe. So it's directly measuring the very small scale shear variance and getting dissipation from that. The blue line is the average. So you consider that to be like observed epsilon dissipation. The black stars are the fine scale parameterization. So assuming that you know things about the larger scale velocity, what dissipation would you predict? The pink plus signs are from coarse graining. So that's using an array of moorings and the horizontal and vertical gradients from that, and using that to estimate the dissipation using this coarse graining method that I mentioned. And then the purple line is this wave-wave method. So that is assuming that your system is governed by weakly nonlinear wave-wave interactions, how much dissipation would you expect to see? And the really awesome and annoying thing is that they all kind of agree. And then the red dots are just some physical bounds on the system. So like, this is the minimum amount of dissipation that could possibly be occurring to account for the amount of kinetic energy you see like changing over time in the internal wave field. And then this would be if all of the internal wave energy was being dissipated on the period of one tide. So like, I guess maybe the setup for this is that we're in a canyon and the internal tide is breaking. So every 6 hours, you have this huge 200-meter tall convective overturn that's creating a lot of mixing. Yeah, so all these different methods sort of agree on the magnitude of dissipation that you would see, but the pathway that that energy takes, they see differently. So this is the scale that energy is being put in. This is the semidiurnal tide, and then this is the buoyancy frequency. And then this is the highest frequency that we can observe. So if you compute the cross scale kinetic and cross frequency kinetic energy flux at each one of these dot dash lines. So like the arrow going across this line, there's 8.8 times 10 to the negative 8 watts per meter squared going across this line. And then if you compare that to its neighbor, the divergence between them must be the energy that is going directly to dissipation from within this bin. So like, this is basically just comparing the pathways energy is taking between coarse graining and the wave-wave method. And one of the fundamental differences between those two methods is that coarse graining allows for strong nonlinearity, while the wave-wave method assumes weak nonlinearity. And the biggest qualitative difference between them is that when you assume weak nonlinearity, you get a much more even distribution of energy transfer from across scales. So like this method, like almost half of the energy has dissipated before you even cross 6 cycles per day, whereas this one is spread a little bit more evenly across the bins. And I wish the bins were the same size and they're in the same place, but they're not. So
And just to understand, so if you added up all of this, it
Yes.
would be the same. So your production, that's equals your production.
So if you
Okay.
yes, if you added up all the purple values, you would get this vertical line, and if you added up the pink values, you would get line. Haley?
Your estimates and your direct contributions in the far on the left.
Mhm.
Seem to, in multiple places, exceed your bounds.
Yes.
You're okay.
Yeah, the bounds are a little hand wavy. I think the main thing I like about the bounds is that it's sort of like a more physical intuition way of saying that like the amount of dissipation that we're predicting lines up pretty well with all of the internal wave energy being dissipated on a period of 1 tidal cycle. So I think that's kind of what I like about the bounds.
It's the fact that your observed dissipation is pretty close to that now. You know, students that are
I think so, yeah. And this is just you know, in this one case where we have this convective tie breaking in a canyon. So it's sort of niche. Yeah. So just to summarize, kinetic energy moves between scales at a direction and rate that corresponds to the physical interactions between those scales. And the kinetic energy cascade is reflected in the spectra of shear and of kinetic energy and wave number and frequency space. So the shape of that spectrum can help us say things about the cascade. Any questions before lunch? Cool. See y'all in an hour. Oh, are there questions? No.
I got that off.